Sensors and transducers. These are the basic input elements of a mechatronic system. As I have said earlier, the sensors produce a signal in correspondence to the quantity to be measured. For example, consider a normal mercury thermometer. In correspondence to the change in temperature, the mercury rises within the calibrated scale and gives the reading to the user. Transducers are also similar to sensors. In fact, both these terms are used as synonyms to each other. However, there is a basic difference in the working of these two. Similar to the sensor, transducers also produces a signal which corresponds to the input physical change. However, the energy form in which the output signal is generated will be different to the input signal. A microphone is an example for a transducer. It converts the input electric signals into a sound energy, which is in a different form, energy form. So unlike the sensors, in transducers, the input signal and the output signal will be in different energy forms, and mostly one of them would be an electric signal. A motor is another example for a transducer, which converts an electrical energy into a motion. To describe the performance of transducers, various terminologies are used. These are the performance terminologies. The first one is the range and span. The range is the limits between which the input can vary, whereas the span is the difference between these two limits. For example, consider an ammeter, two ammeters having limits of 0 to 5 ampere, then 5 to 10 amperes. Now, the span of these two ammeters are the same, which is 5 ampere. However, the limits between which the input can vary are different. Thus, the transducer can have the same span but different range. Now, error is the difference between the measured value and the true absolute value of the quantity to be measured. The next one is the accuracy. It is the closeness of the measured value to the absolute true value of the quantity. Higher the error, lower will be the accuracy of the measurement. The next one is the sensitivity. It is the amount of output produced for the application of a unit input. Higher the sensitivity of a transducer or a sensor, more will be the output produced by unit input, which would be helpful in the calibration. However, higher sensitivity means the transducer or the sensor will be more prone to the external disturbances, which could affect the accuracy of the measurement. Now, hysteresis error. We know that the transducer or the sensor should give same output value for a same input value. But depending on the manner in which the input was applied, the transducer or the sensor gives different output values. This difference in the output values for a same input quantity depending on the application of the input, this is known as the hysteresis error. To elaborate, consider the graph shown on the slide. It shows the output to a input graph of a transducer. Now we can see that it shows two graphs where the input is applied by constant increasing and also when the input was applied by constant decrease. Now when we check the graph, we can see that for the same input quantity, the output is different for both the cases. The difference between these two outputs for the same input value is known as the hysteresis error. The next one is the nonlinearity error. The transducers are assumed to have a linear relationship between the input and output. This means that when we plot the output versus the input, it will give a straight line. However, most of the transducers does not follow this linear relationship. Rather, they follow a non-linear relationship, which means that the graph would be a curve rather than a straight line. The nonlinearity error arises due to this assumption of linear relationship between the input and output. It can be defined as the difference between the actual line and the assumed line, as shown from the graphs. Now, the linear relationship can be assumed by different methods. The straight line can be plotted by simply joining the two ends of the actual curve. In the second method, the method of least squares can be followed, where all the points on the actual curve are assumed to be equally likely to be on the error. Now, the third method is similar to the least square method, but the linear line will be passing through the 0 point of the actual curve. Repeatability or reproducibility is similar to the concept of precision. It is the ability to give the same output for repeated applications of the same input value. In a pure ideal case, the transducer should be able to give the same output for the same input. However, this will not be true and there will be differences. Now, the repeatability is given by the maximum value of the output minus the minimum value of the output obtained by the full range input value into 100. Stability. So, when an input is applied constantly over a period of time, if the transducer gives the same output, then it is said to be stable. In some cases, due to external factors, even when there is zero input, the output is a non-zero value, and this is termed as the zero drift. Dead band or dead time. Now, whenever we apply an input, an output occurs. However, in some cases, there won't be any output for a application of an input. Now, this value of the input for which there is no output is called as the dead band. Now, the time from the application of an input until there is a response from the transducer, it is known as the dead time. Resolution. It is the amount of input value that will produce an uh, observable change in the output. Thus, higher the resolution, the lower will be the input value required to produce an output. Now, we know that the transducers and sensors produce an output signal in correspondence to the change in input value. Now, this output signal will be transferred to a circuit or a microprocessor for further processing. However, there will be an associated resistance for the flow of this current or signal into the next circuit. Now, this value is known as the output impedance. It is the measure of opposition to this current flow or signal flow to the adjacent circuit.